Throughout our studies of numerical integration, we have been using sin x as a common function to compare the accuracy of various methods. Specifically, we have been trying to find the area shown in red by using our numerical methods. Then, we have been comparing those to the known value to see how well they perform. For Simpson's rule, we are going to start by splitting the interval into 3 panels and adding up the individual areas to find total area. These happen to be parabolic curves. They don't match the sine curve exactly, but they are a closer fit than an equal number of trapezoids would be. Based on that reasoning, this should give us a final answer closer to the true value. Let's find out. Here is Simpson's rule. We derived this in the previous lesson. I've just presented it now for convenient reference. Notice that every odd value is multiplied by 4, and every even value, except f0 and fn, are multiplied by 2. This is the data table for y equals sin x. Fairly straightforward. Now I'm going to add a 4th column for weights. These are the 2's and 4's we just mentioned, except for 1's on the endpoints. Just notice that it alternates 4, 2, 4, 2, 4. The 5th column is the product of y and the weight. The sum of the 5th column is boxed in red. All this is multiplied by mesh size h and divided by 3. The final answer is boxed in green. What if we want to use 6 panels instead of 3? Then we have to double the number of data points from 6 to 12. The data table for y equals sin x is shown here. As before, I add a 4th column for weight. Same thing with alternating 4's and 2's, except 1's for f0 and f12. The 5th column is the product of the 3rd and 4th column. Boxed in red is the sum of those values. Then I multiply that by the mesh size, this time 0.5 instead of 1, and divide by 3. I could do the same for 12 and 24 panels. Those results are shown here in green. As we've done in previous lessons, the error is computed in the final column. Error is the difference between Simpson's rule and the true value. The data tables double each time and become too long to conveniently show on the screen. The same pattern applies, so I encourage you to compute these values for yourself and compare your results to mine. We've seen this plenty of times also. Dividing subsequent error terms, it would appear that Simpson's rule is indeed 4th order, as it should be according to the Taylor series derivation. It should be noted that throughout these lessons, I have retained the full number of digits that Microsoft Excel can handle in each calculation. However, the data tables have been rounded to a limited number of digits for ease of representation on the screen. On this screen, I have summarized the results from previous lessons. That includes the trapezoid rules, both with and without end correction. Below them is Simpson's rule. The method on the left is only 2nd order, whereas those on the right are both 4th order. Compare these numbers to the true value of the integral, shown in the bottom left.